Okay, this is my lab one report. Okay, so this is the written. Okay, so first let's say, okay, so to introduce this lab, I rolled a toy car that was initially at rest over a smooth surface in order to witness an example of constant velocity motion. Next, I analyzed the video of that car with the tracker software and constructed a computational model via code that predicts the position of the toy car based upon its initial velocity that I inputted. The experimental values graph the actual position data points of the car, while the computational model graph the path the car would take in an ideal world without friction and other forces acting on the car. Lastly, I compared the experiment and computational model graphs, position graphs via a spreadsheet. The purpose of this lab is to model a real-life instance of near constant velocity and to construct experimental and computational of models of this motion. To relate our models, next to relate our models to the fundamental physics principle of Newton's second law, which states that net force is equal to mass times acceleration. And lastly, we compared our computational and experimental models to note the differences in them. Lastly, I wanted to state that we consider our system in this case to be the toy car and the surroundings to be everything outside that. So this is just the written form of that. Okay, so let's look at this video. Okay, that was the video. Hold on. Okay, so this is my observed position for the portion that the small portion I chose from that video. As you can see, it's approximately constant, not exactly, but we'll discuss that. This is the predicted position based upon that initial velocity. As you can see, it increases at a constant rate, which is what would be predicted to happen in an ideal world with no friction. So now I compared those two graphs. As you can see, the position just keeps on going and going and going and going. This one is different. You can see the it doesn't go at such a linear rate. So therefore, the experimental and model position versus time graphs do differ in this way, as we can clearly see. So the conclusions of this, the observational and computational graphs are slightly different. The reason for this is due to Newton's second law, which states that velocity only changes when a net force acts on our system, toy car. The computational model of the car has a net force of 0 because it is in an ideal world. However, the observational model is in the real world, where we have outside forces acting on our system. The primary force that acts in the system will be friction, which ends up causing our velocity to be non-constant, as you can see. It changes at a non-constant rate, and we have acceleration or deceleration. Though I would note that the part in it is approximately constant for our purposes. Therefore, we concluded that with the help of Newton's second law, we know that an object will continue to move with a constant velocity if not acted upon by an outside force, as you can see by the theoretical model. However, in the real world, it accelerates when there is a net force acting on our system, or in this case, that would be friction, as you can see from the real world graph, the red one. There was an outside force acting upon it, so the velocity did change, which is the derivative of these two graphs. So just the written form. Next, lastly, I'm going to discuss some error. There were potential sources of error, and I'll discuss two of them. Firstly, the toy car was rolled at an angle, which means that the coordinate axis had to be rotated, which could have led to some problems when graphing it, some slight problems, nothing too big. Second would be human error, which causes mismeasurements during our experiment. So human measurement is not perfect, which leads to some potential error. So for the what if question, I would say, had we used a different choice of axis, the actual numbers in my position graph would be different. For example, this blue one may be going in a negative direction, and the same with the red one, it would be negated perhaps. However, what would stay the same is that the linear aspect of this would be the same. So it would be still going at a constant. That would not change. It would still be moving at some constant velocity. Our computational model and our experimental model would be moving at approximately constant velocity. So yeah, so that's what would be different, is that the actual numbers and actual sign of it would be different, whether it's positive or negative. But what would stay the same is the very important fact that it is constant in the case of the computational model and approximately constant in the case of the experimental model. So for the last question, it discusses can we know all the forces being added up? I said it is not necessarily possible to know exactly how many forces are being added up together. What we do know is that the net force acting on the toy car is 0. So that means the sum of all forces must add up to 0. And we know that since the net force is 0, there's constant velocity, and all forces acting on the system are equal in magnitude to that friction force that slows the car down, but all these other forces point in the opposite direction. So based on our current knowledge, all we know is that all these forces, whatever they are, they sum up to counteract the friction force by exactly being equal in magnitude and opposing the direction. So that can either be one force that exactly points in the opposite direction or multiple forces. We don't know. What we do know is that there is it moving at a constant velocity. The toy car is moving at a constant velocity, so that means the net force is 0, and the sum of all the total forces, the vector sum of them, would be 0. Thank you. So I have also written this down in case you wanted to see. I've answered the two what if question and the other question, and yeah. So if you need, this just needs